Good morning, sir. Our topic for today is all about orbits and cyclic. The orbit of an element x in X is the set of elements in X to which X can be moved by the elements of G. The orbit of X is denoted by Gx. The defining properties of a group guarantee that the set of orbits of X under the action of G form a partition of X. How do you find the orbit of a permutation? The orbit of an element X and X is apparently simply the set of points in the cycle of containing X. A cyclic permutation of degree n of a set S having n distinct elements, and if it is possible to arrange some of the elements of a set is in a row such that n, the follow image of each element in this row is the element following it, and the follow image of the last element is the row is the first element, and remaining elements of the set S remain invariant under F. Then F is called a cycle permutation or a cycle of length M. The number of objects permuted by the cycle is called the length of a cycle. This by the cycle of the length of E, we mean a permutation in which the image of each element remain unchanged under a permutation F. Consequently, the cycle permutation of length 1 is the identity permutation. Orbits, its permutation Q of A set A determine a natural partition of A into cells with the property that A, B, and A are in the same cell if and only if B equals to Q to the power of n times A for some n and Z. This gives natural equivalence relation. One can easily check reflexive symmetric transitivity. Let Q be a permutation of A set A. The equivalence classes in A determined by the equivalence relation above are the orbits of A. Cycles. Suppose A equals to 1, 2, n, and we consider elements of the symmetric group Sn. Let Q equals to 1, 2, 3, 4, 5, 6, 7, 8, and 3, 8, 6, 7, 4, 1, 5, 2. A permutation of Q S n is a cycle if it has at most one orbit containing more than one element. The length of a cycle is the number of elements in each largest orbit. Each cycle can be represented by a permutation. For instance, U equals to 1, 2, 3, 4, 5, 6, 7, 8, 3, 2, 6, 4, 5, 1, 7, 8. We introduce a single row cycle notation. We write it as U equals 1, 2, 1, 3, 6. Using cycle notation, we see that Q can be written as a product of cycle. Q equals to 1, 3, 6, 2, 8, 4, 7, 5. These cycles are disjoint, meaning that any integer is moved by at most one of these cycles.
Good day everyone, I am Almi Salio. So this is the continuation of our report about orbits and cycles. So this is some terms that you must need to remember. Permutation is more or less a shift of a number. 1. Orbits are subset of permutation that cycle through one another. 1. Cycles show the order of the orbits. And fourth one, orbits cannot be permutation or cycles. Let's proceed to the example. Find the orbits of a permutation. So this is the given permutation. We have 1, 2, 3, 4, 5, 6, 7, and 8. Then 5, 6, 2, 4, 8, 3, 1, and 7. So as we can see, 1 goes to 5, 5 goes to 8, 8 goes to 7, 7 goes to 1, then 2 goes to 6, 6 goes to 3, 3 goes to 2, then 4 by itself. So the orbits are 1, 5, 8, 7, 2, 6, 3, then 4. Let's proceed to the second example. Find the orbits of the permutation. So again and again we have 1, 2, 3, 4, 5, 6, 7, and 8. Then 3, 8, 6, 5, 7 rather, 4, 1, 5, and 2. So as we can see, 1 goes to 3, 3 goes to 6, then 6 goes to 1. Then 2 goes to 8, 8 goes to 2, then 4 goes to 7, 7 goes to 5, then 5 goes to 4. So therefore, the orbits are 1, 3, 6, then 2 and 8, then 7, 4, 7, and 5. So let's proceed to the cycle. So this is the given permutation. So the upper side called inputs, then this side is called outputs. So let's proceed to the example. We have 1, 2, 3, 4, and 5, then 3, 5, 4, 1, and 2. If we are going to start with 1, so 1 goes to 3, then 3 goes to 4, then 4 goes to 1. So like this one, 1 goes to 3, 3 goes to 4, then 4 goes to 1 again. So this one, 2 goes to 5, then 5 goes to 2. So 1, 3, and 4 called 3 cycles because we can write it like here. We can write it like this one. 1 goes to 3, 3 goes to 4, 4 goes to 1, then 4 goes to 3, like this, and so on. This one is 2 cycles, then another 2 cycles, another term is transposition. Important note, cycle with no numbers in common can be rearranged. Cycles with no number in common commute with each other. Like for example, A is equals 1, 2, 3, 3, 2, and 1. Then letter B, 1, 2, 3, then 3, 2, 1. So A is equals 1 goes to 3, 3 goes to 2, then 2 goes to 1. Then in this side, 1 goes to 3, then 3 goes to 1. So let's multiply A by V. It is equals 1, 3, and 2, then multiply by 1 and 3 is equals 1 and 2. Then let's multiply B by A. Let's copy the 1 and 3, then 1, 3, and 2. So 8 multiplied by A, B multiplied by A is equals 2 and 3. So that A multiplied by B is not equal to B multiplied by A. Let's proceed to the second example under cycles. Express the permutation of the given elements 1, 2, 3, 4, 5, 6, 7, and 8 as a product of disjoint cycles, then as a product of transposition. So this is the given permutation. We have 1, 2, 3, 4, 5, 6, 7, and 8. Then 3, 6, 4, 1, 8, 2, 5, and 7. So as we can see, 1 goes to 3, 3 goes to 4, then 2 goes to 6, 6 goes to 2. Then 5 goes to 6, the 8 rather, 8 goes to 7. So a transposition is a cycle of length 2, looks like A and B. So we are going to put it here, 1, 3, 4, 2, and 6, then 5, 8, and 7. So it is equals to 1 to 4, 1 to 3, then just copy the 2 and 6, then 5 to 7, 5 to 8.